If a normal ship drives into Arctic sea ice, the problem is not power, it is geometry. A sharp bow that slices cleanly through water becomes useless the moment the water turns solid. The ship stops. The ice does not. But an icebreaker is built to do something that sounds completely wrong. It climbs onto the ice, and then it lets gravity attack the ice for it. Chapter 1. Why normal ships fail. A conventional ship is optimized for fluid flow. Its bow is designed to separate water, reduce resistance, and keep the vessel stable at speed. That same geometry performs badly in heavy sea ice. Instead of riding upward, the hull drives forward into a rigid sheet and gets trapped between compressive forces from both sides. Forward thrust stops producing progress. It starts producing stress. Side pressure from surrounding ice acting on the hull. This is why ordinary merchant ships can become immobilized in pack ice even when their engines are still delivering power. More thrust does not solve the problem. It can make the structural situation worse. Icebreakers solve that by changing the force path completely. But the real trick is not the engine, it is the bow. Chapter 2. The spoon bow. An icebreaker uses a rounded, sloped bow, often described as a spoon bow. Instead of punching straight into the ice, the hull rides up onto the surface. That converts forward motion into vertical loading. Hull geometry designed to ride onto the ice surface. Once the icebreaker's weight transfers onto the ice, the challenge shifts. It's no longer about impact or collision. Instead, the issue becomes one of structural failure, as the ice must bend and fracture under the vessel's massive downward load. A large nuclear icebreaker weighs more than 33,000 tons. That mass is now acting through a relatively small contact zone. And that is where the ice begins to lose. Flexure failure demonstration. Ice rarely breaks from direct impact. Instead, failure occurs through bending. As an icebreaker rides upward, its weight pushes the ice sheet downward, creating tensile stress underneath. When this stress surpasses the ice's structural strength, the sheet suddenly fractures in a single sharp event. Engineers refer to this bending and snapping process as flexure failure, which is the primary mechanism by which ice yields to massive vessels. Ice bending until it fractures under load. But ship mass alone still is not enough, because Arctic ice is not uniform. Chapter 3. Ballast makes the ship heavier when it matters. Sea ice varies in thickness, density, and surface roughness. To adapt, the icebreaker must adjust the force it applies to the ice. This is achieved through ballast systems, which control the ship's weight distribution and pressure on the ice, changing ship depth in the water by adjusting ballast. Icebreakers are equipped with large ballast tanks that can be filled or adjusted to change draft and trim. Filling the tanks makes the vessel sit deeper, while shifting trim alters the angle of contact. This allows the ship to precisely control the force it applies to the ice, increasing pressure exactly when conditions demand it. Icebreakers differ from ordinary ships, functioning more like moving structural machines. They are not merely floating. Instead, they actively adjust their weight, trim, and contact with the ice, precisely controlling how they interact with a solid surface to efficiently brake and ride over ice sheets. But pressing onto the ice is only half the battle. The ship still has to keep moving. Chapter 4. Why nuclear propulsion matters. Braking and riding over ice is a continuous process. The vessel must push forward through resistance, fragmented ice, drag, and variable surface conditions. To sustain this relentless power and maintain consistent progress in the Arctic, modern heavy icebreakers rely on high-output nuclear propulsion systems. Compact marine reactor used in modern Russian nuclear icebreakers. The key advantage is more than extended range. It is continuous, sustained power. A nuclear reactor can supply enormous propulsion loads for long durations without the limitations of conventional fuel systems, allowing modern icebreakers to operate efficiently in the Arctic for extended missions. In thick ice, propulsion is not a one-time effort. It is a continuous process. The vessel constantly loses energy to hull friction, broken ice, propeller load, and repeated climb and fracture cycles. Nuclear propulsion provides the power and endurance engineers need to maintain this relentless cycle, enabling icebreakers to operate efficiently in extreme Arctic conditions. Nuclear propulsion gives engineers the endurance to keep that cycle going. And because propulsion power is delivered through robust marine drive systems, the ship can maintain the torque needed to keep forcing the bow back onto fresh ice. This is what separates spectacle from engineering. The dramatic cracking sound is only the visible part. The real machine is the power system underneath it. But breaking the ice creates a new problem immediately. Now the ship has to survive its own debris field. Chapter 5. Friction, Adhesion, and Ice Clearance. After the ice sheet fractures, the vessel navigates through broken slabs, compacted fragments, slush, and pressure ridges. This chaotic mixture can scrape the hull, stick to surfaces, jam movement, and increase resistance, requiring continuous propulsion adjustments to maintain forward progress through the Arctic ice field. Ice sticking to hull surfaces and increasing resistance. To manage friction and prevent jamming, icebreakers employ specialized hull coatings, smooth contact surfaces, and optimized hull shapes. These design features guide broken ice away from the sides, reducing resistance and allowing the vessel to maintain steady forward movement even through fragmented, compacted, or slushy Arctic ice. Friction control matters because a ship that fractures the sheet but cannot clear the debris will still lose momentum. In other words, the engineering problem is not only how to crack the ice, it is how to stop the broken ice from trapping the ship afterwards. Hull geometry, ballast control, propulsion, and low-friction surfaces are all working on the same objective: maintain forward progress through a material that behaves like both a brittle plate and a moving obstacle field. And that is why an icebreaker is not simply a stronger ship, it is a ship designed around force conversion. A nuclear icebreaker does not defeat Arctic ice by slicing through it. It defeats ice by changing the geometry of the encounter. The bow rides up. The ship's mass loads the sheet bends, the sheet fails, and sustained propulsion keeps the process repeating in one of the harshest operating environments on Earth. This is naval engineering at its most physical. Not speed, not elegance. Mass, load path, torque, and controlled fracture. But naval engineering does not always solve resistance by crushing it. Sometimes it solves the opposite problem. How to accelerate a 30-ton aircraft from 0 to flight speed in seconds from the deck of a moving ship. To see how carrier catapult systems turn stored energy into launch force, watch the next briefing on your screen now. Dismissed.